Thank you for the introduction. Thank you very much for the opportunity to speak. I'm excited to share with you some research that Raphael and I are working on. We're just putting the finishing touches on it, and it's entitled Islands in Closed and Open Universes. So as many of you are probably aware, if you've been following the recent literature, the last couple years there has been a lot of excitement about computing the entropy of Hawking radiation, which is called the page curve. What you expect, a black hole that's evaporating, that's emitting Hawking radiation, you expect that its entropy of this Hawking radiation should follow a particular curve, which is called the page curve. And over the past couple years, there's been a lot of progress in understanding how to derive the page curve using a particular technique, the quantum extremal surface prescription. And this is a prescription for computing entropies that I'll explain more detail in a moment. It is an ADS-CFT relation, or you can view it as a saddle point approximation of the gravitational path integral. But one thing that's really exciting about this recent work using the quantum extremal surface prescription to compute the page curve is it seems like this calculation is capturing something very interesting about quantum gravity, the page curve, from a semi-classical analysis. So in the quantum extremal surface prescription, the bulk state is computed semi-classically. I'll explain that in more detail in a moment. But this seems like something very exciting. Perhaps there's an in to understanding quantum gravity here that we didn't realize we had before. And so a natural question is whether we can take the insights that we found from these calculations and apply them to other scenarios and see if we could learn something about quantum gravity in other scenarios, one of them being cosmology. Should I remove this? Is this distracting? This just popped up.
I think it's not showing on the actual view, so I think it should be fine.
Well, okay, I'll oh, is someone talking on there? No, it's just me. Okay. Yeah. Okay, great. I'm not sure if I'll see comments on there. Well, one of the questions you could ask is whether we could learn something from these insights in the context of cosmology. And so first, let me take a step back and explain a little bit more in detail what the quantum extremal surface prescription is, in case you need a refresher or haven't seen it before. So the quantum extremal surface prescription, as I mentioned at the beginning, can be viewed as an ADS-CFT relationship. I'll remind you that ADS-CFT is this mathematical duality between quantum gravity in an ADS spacetime and a non-gravitational theory, a CFT, where the ADS spacetime is in one higher dimension than the CFT. And the quantum extremal surface prescription is a method for computing entropies in boundary regions, so this is the boundary theory, in terms of quantities in the bulk theory, which is this one here. So it can compute entropies of the boundary region in terms of quantities in the bulk. And here I have a picture. This outer ring is the boundary theory. This interior is the bulk. So the quantum extremal surface prescription tells us that if we would like to compute the entropy of this region R on the boundary, we'll need to compute a generalized entropy, where the generalized entropy of a particular surface is defined as the area of that surface plus the entropy of the matter enclosed by that surface. And the quantum extremal surface prescription tells you that to compute this entropy of R here, we need to find a special surface and then compute the generalized entropy of that surface. And that gives us the entropy of the boundary region. And this special surface needs to satisfy a couple constraints. It needs to be homologous with the region R. It needs to be stationary with respect to the generalized entropy. The generalized entropy is stationary. And then amongst all surfaces that satisfies those conditions, it needs to be the one with the smallest generalized entropy. So that's the quantum extremal surface prescription in terms of the quantum extremal surface gamma, which is what I'm calling it here. You can also, kind of just a different perspective, think of it in terms of this interior region here, enclosed by gamma, which is called the entanglement wedge of R. It's just kind of a different perspective. In that case, the entropy of the boundary region R is the generalized entropy of the entanglement wedge, which is this region here. And then the generalized entropy of the entanglement wedge is defined as the area of the boundary of the entanglement wedge plus the entropy enclosed in the entanglement wedge. And then, of course, the entanglement wedge needs to obey these various conditions so that it's the same prescription as the previous statement of it. Yes?
So, out of ignorance, this entropy in the entanglement wedge, are there cases where it's much more dominant than the entropy of the area?
This here?
Subdominant, same?
Yes. So, in fact, that is part of those calculations that I talked about, calculating the page curve. Part of those, the key part of those calculations involves checking when the area term and the matter enclosed term, which of them are dominant. This term?
Yeah.
Well, I mean, you could have no boundary. Then A would be 0. So I guess, yeah.
That's the only case, right?
I think so. But that's the important case in the calculation that I was referring to.
Sorry, but what you just pointed out is that in examples where there is an island,
Yes.
that's an example where S is bigger than A or
So this is not just some small fluctuation.
I mean, the S of the island is bigger. Of course, the S of the whole entanglement wedge is not.
Is that the Gaussian part where S has to be always absorbed by A?
But it's not that, but sorry, I just mean like you have an island
Great one.
and there's a lot of
Yes.
Hawking
Okay,
radiation in
thank
it.
you.
Yeah.
Okay. So as Raphael mentioned islands, so that's where I'm going next. But so one of the key insight, perhaps you could say, in these calculations for computing the page curve was realizing that at a particular time, there is a so-called entanglement island, which contributes to the entanglement wedge. This entanglement island is a disconnected portion of the entanglement wedge. It's disconnected from the region R that is being computed. And in the case that they were looking at, the quantum extremal surface prescription reduces to this particular rule called the island rule. And this is the case where there is a gravitating spacetime and a non-gravitating spacetime, and the region R for which you're computing the entropy using the quantum extremal surface prescription is in fact a region inside this non-gravitating spacetime. And in this case, the quantum extremal surface prescription reduces to the following. The entanglement wedge of this region R is given by R itself plus potentially an island, a so-called island, in the gravitating spacetime. This could be the empty set. And then the generalized entropy still needs to be stationary, and that island needs to be chosen such that the generalized entropy is minimized, just like before. So the appearance of the island being a crucial part of the page curve analysis can make you ask this question whether we could understand something about, take those insights and understand something about cosmology by asking when those islands could appear in cosmological spacetimes. So this is a question that this paper here, Hartman et al. In 2020, they asked this question and approached it by kind of turning the question around. Where normally when you're using the quantum extremal surface prescription, you're trying to pick a reference region R, and then you're asking what is the entanglement wedge for R. And then you go and look if there's an island. But in this paper, and also for what we're going to do, the question is instead, when is it possible for a region in this cosmological spacetime to be an island for some region in a reference spacetime? And this paper here looked at a particular model, cosmological model, flat FRW, and found some conditions under which, some necessary conditions for islands to appear, and then also went and checked to see in some cases, or checked to see in the flat FRW case, what universes could have islands. So they found some necessary conditions and then checked to see where all of those necessary conditions could be satisfied at once. And just a reminder, in case you're not sure what FRW universes are, very briefly, FRW universes are ones that are homogeneous, so they're the same everywhere, and then isotropic, so they have no preferred directions. And the most general metric that satisfies these conditions is the FRW metric, which takes this form here. And you can see that this part is, so this chi is the co-moving coordinate, it's the radial coordinate. And then this part here is one of three possible functions depending on which of these three geometries you'd like to consider. So these are all consistent with these assumptions. These are just three options. And you can see that if you choose flat, you end up with a sphere here, and then closed and open, you end up with closed geometry sphere and then open geometry sphere. And the size of this sphere is then dictated by this A, which is the scale factor. Yes?
It's a little unconventional calling that a sphere and all.
Oh, well, it's spherically symmetrical.
No, but I mean, this is Euclidean space in the flat case, and it's a hyperboloid in the case.
That's okay. So yeah, maybe the terminology is not exactly. But so the scale factor is what determines the size of the universe at a particular time. And the scale factor's dynamics are determined by the Friedman equation, which is the following. So the Friedman equation has various parts that depend on the content of the universe. So in the Hartman et al. Paper, and then also what we'll do, we'll assume there's radiation, and that contributes to this term here. If there's a cosmological constant, there's another term in the equation, which goes to 0 in the case where the cosmological constant is 0. And the sign here corresponds to the sign of the cosmological constant. And then this last term here is the curvature term. And here are some definitions of the various quantities. So you can see the energy density of the radiation shows up in the radiation term. There's lambda shows up in lambda, or in the cosmological term, cosmological constant term. And this final piece here has three options depending, again, if you're going to choose the flat, closed, or open geometries. And the Hartman et al. Paper, which our work is kind of an extension of, the Hartman et al. Paper considers just the case where the universe is flat. And so our question, as you can probably guess from the title of the talk, is what happens if you relax this assumption and look at closed and open universes? So having described what the question is, and the question is, when is a region in a particular cosmological universe possibly an island for some reference region? The Hartman et al. Paper then went on to derive some necessary conditions that a region must satisfy for it to be an island. And those conditions all still are relevant for our case, where we're asking about closed and open universes. But we also have a fourth necessary condition, which only appears in the case where the universe is closed. It's only relevant for that case. So let me show you what the different conditions are. So the first one is a consequence of the fact that there is an area cost to adding an island to the entanglement wedge. So if you remember, the generalized entropy has the area part and then the matter enclosed part. And so if you're going to add an island to the entanglement wedge, that will add the area of that island to the generalized entropy. So this can only ever be favorable, because remember we're trying to minimize the generalized entropy as well. This can only ever be favorable if adding the island is worth the area cost, in that it decreases the matter entropy term enough. And this will be true, for example, if there's a bunch of entanglement between the gravitating spacetime and then the reference spacetime. And so that translates into a requirement on the matter entropy inside the island. So the matter entropy in the island needs to exceed the area cost of the island. So that's the first condition that Hartman et al. Paper calls the violation of the Bekenstein bound. The second condition is a consequence of the fact that the island together with the reference region are supposed to be quantum extremal. And that was part of the definition in the quantum extremal surface prescription. And so they are supposed to be quantum extremal. And if you rephrase this quantum extremality condition in terms of the mutual information between I and R, you can show, which the Hartman et al. Paper did, you can show that this condition translates into a requirement on how SGen changes, on how the generalized entropy changes under shape deformations of I. It seems it's natural because the generalized entropy has the area terms, the shape deformations of I. That's what it means for it to be stationary under shape deformations. Sorry, what I'm saying is that the quantum extremality condition is a statement about shape deformation. So it makes sense that that would then translate into some condition on the shape deformations. And indeed, you can show that the condition translates into the fact that the island must have a positive outgoing quantum expansion, where the quantum expansion is just roughly how the generalized entropy changes under the shape deformation. And then it needs to have a negative ingoing future quantum expansion. And so those together, those conditions together, are just the definition of quantum normal. And so the second condition is that the island I must be quantum normal. So then the third condition is a consequence of the assumption that the Hartman et al. Paper makes and that we will make as well, that the two universes here are together in a pure state. And so G, which is the complement of I, this area outside of I, and Q, which is the complement of R, those should also together be quantum extremal. And so that translates into an analogous condition on G being this complement of I. So the third condition is that G must also be quantum normal. So those are the three conditions that were relevant in the case of flat space. So now there's one more condition that becomes relevant if you're considering subsets of closed universes. So in the case where the universe is closed, the entire Cauchy slice of the universe is potentially an island candidate. And you can, in fact, show that such a Cauchy slice, the whole Cauchy slice, trivially satisfies all three other conditions. So it doesn't have a boundary, so there's nothing to deform for the second two conditions. And then the area boundary 0, first one. And so because the whole Cauchy slice always is an island candidate according to those other three conditions, if a subset of the universe were to be an island, it would have to be a better candidate than the entire universe. When I say entire universe, I mean a Cauchy slice. Sometimes I'll say entire universe, but I mean a Cauchy slice. And so for that to be true, that translates into a requirement on the matter entropy enclosed in this complement of I, region G. So we end up with a complementary condition to the first condition for the case of subsets of closed universes. And I called it better than everything. It needs to be a better candidate than the entire universe, which is always a viable candidate. So just in summary, these are the 4 necessary conditions that are relevant in the case that we will consider. This one is relevant in some of them. So we have these 2, which are kind of complements of each other, and then these 2, which are also complements of each other. Yes?
So for clarification, are the first 3 conditions sort of like generally something that has to be true? Not only for FRW, right?
Yes, so we haven't, in deriving these necessary conditions, they haven't yet specialized to the FRW case.
And it's also true for condition 4 then, that this is true in general?
Yes, it will, if you have a closed universe, yeah.
Okay.
Yeah. So having derived these conditions, the Hartman et al. Paper then would like to ask, when is it possible for these conditions to be simultaneously satisfied? And you might notice that, that in order for that first condition to be satisfied at all, there needs to be something that makes up for that area cost. And so you might ask, what could possibly be the source of the entanglement required for the island to be favorable? And the approach that the Hartman et al. Paper takes, and then we will also take, is not to worry about what the source of that entanglement is, and instead we'll just assume a particular construction which has a bunch of entanglement, which is favorable for islands. And then if islands are still not possible, that would already be interesting, if they're not possible under favorable assumptions. But it's a good question, what could be the source of the entanglement required for the islands to be favorable? But so the particular construction that the Hartman et al. Paper uses, and then that we use, which is one that's very similar, is to start with 2 copies of a non-gravitating spacetime and construct the thermal field double with those 2 copies. So this is a cartoon just to kind of show that there's entanglement between the 2 copies. And then in order to get this gravitating spacetime, we need to do a conformal transformation to produce it, to get the scale factor. So this is the universe that the FRW metric applies to. So in the original paper, the FRW metric, of course, is just the flat space metric, but then in ours, we consider general metrics, or general FRW metric.
Just one question.
Mm-hmm.
So the fourth condition, is it for the when G is a quantum normal?
Sorry, could you say that?
The fourth condition, is it when G is the quantum normal?
The 4th condition is that a subset of a closed universe has to have the complement of I, the matter entropy in the complement of I must exceed the area. So I don't. So it is.
It only applies to closed universes.
It only applies to closed universes. Yes.
I mean, you could say that it applies to all universes, but it's trivially satisfied.
Yeah. So then the question, the next step is to ask, when is it possible for this region in this gravitating spacetime, FRW spacetime, to satisfy all of those conditions simultaneously? And the island candidates that we'll consider are spherically symmetrical islands that are centered in the origin. And so I'll just show you the results from the flat space paper. So the flat space paper found that islands are only possible in the case where the cosmological constant is negative. And they have to exist around the turnaround time. Near the turnaround time. The turnaround time is where the universe starts recollapsing. And they also need to be large. So those are the results from the flat space paper. So now we'd like to ask, what if we turn on curvature and see what the results are, see if they're different? So I'm going to show you the general procedure for how you go through and check the different conditions. I'll show you the general procedure, and then I'll show how it goes for a couple examples, and then I'll just report the results for the rest of them. So the first step in our search for islands in closed and open universes is to restrict to time-symmetric slices. So slices that we're calling a turnaround time. And the reason we're doing this, well, it simplifies the analysis, and the reason that it should be all right is far away from the time-symmetric slice, the stationarity in the t direction is ruled out, and so that would violate quantum extremality, and you recall that we need to have quantum extremality for the islands. So we can just restrict our search to time-symmetric slices. And that'll give us some more specialized versions of the conditions. I just kind of put them up here so you could see them, but you don't really need to remember the exact details of the expressions. But the conditions all reduce to these different forms in the case where we've restricted to time-symmetric slices. So you can see they'll depend on the volumes and the areas, which will depend on, the precise form of those will depend on if we're looking at a closed or open geometry. And we also need the scale factor at the turnaround time. And so,
Can you say what S sub C is?
yes, S sub C is the co-moving entropy density. So the entropy density and then is related to the entropy density by a factor of A cubed. And yeah, all of these sub C's, these are all of the co-moving quantities. And so they're all related to the physical quantities by factors of A cubed in the volume case or A squared in the area case.
The turnaround time is the time when the universe starts to collapse?
Yes, when it starts to recollapse. Sorry, what?
In the closed case or in general?
In general.
It could also be the time when it bounces at a specific state.
Yeah, it's just a time where the scale factor has derivative 0.
What's the Hubble?
The derivative of the scale.
The derivative scale factor is 0, yeah.
Is it obvious that apart from turnaround time, there is no extremality?
So if you look at the contributions, I guess there isn't a quantum contribution that should be big enough to make up for the change of the area far away from the turnaround time. And there should be a small area close to the turnaround time where this isn't valid, like when the classical expansion is of order G. Yeah.
This is a natural case to look at.
Hmm?
I agree that this is not a natural case to look at.
I think the distinction you want to make is between, so that the sort of general magnitude of the quantum correction can be very large, which you know, in a large region in the universe, just because there's a lot of entropy, the derivative of the volume goes like R squared, let's say in a flat geometry, the derivative of the area only goes like R, so you can achieve stationarity just by looking at very large regions. But what matters for the stationarity in T is the difference of the quantum correction in the future direction and in the past direction. So if you look at, it's very hard to get those to differ by a large amount. So that's the reason why it's hard to get away from the turnaround time.
Yeah, maybe obvious. I mean, it's just time evolution of radiation, for example, and the scale factor, but it's not immediately obvious.
I did also, I guess I don't have it here. I did some numerical calculations that were exact, and it did look like that there shouldn't be any overlap in those two conditions away from far from the turnaround time. So, okay. So once we've restricted to time-symmetric slices, this will apply to all of the cases. And when I say case, I mean whether it's open or closed and what the sign of lambda is. But then for each case, we will need to find the scale factor at the turnaround time, which I mentioned you can just find by setting A dot to 0. So sometimes it will simplify the analysis somewhat to separate into regimes based on the relative sizes of T lambda and Tc. So T lambda and Tc have physical interpretations as the timescales at which lambda starts to dominate for T lambda and curvature starts to dominate for Tc. And so sometimes it just simplifies the expression for A. A0 if you look at different regimes. So then, having found that A0, we can stick it into the time-symmetric slice versions of the conditions and consider a spherical island candidate with radius chi and check to see where the conditions can all be simultaneously satisfied. So just put this picture up again. So spherically symmetrical island candidate with radius chi, and then ask where all the conditions can be satisfied, if anywhere. And then for the closed case, just a heads up, for the closed case, it will involve looking at proper subsets of the universe and the entire Cauchy slice as in different cases. So we have that extra fourth condition. So then, once we've checked all the conditions, if we find some region where I does satisfy all of the conditions simultaneously, then we'll check to see if there is a region in the reference spacetime for which I is an island. So now I'll show you how this goes for the closed lambda equals 0 and closed lambda is negative cases, and then I'll show you what the rest of the results are. So we already restricted to time-symmetric slices by finding those forms of the conditions, the special forms of the conditions. So now we're looking at lambda equals 0 in a closed universe. And at the turnaround time, A dot being 0 just implies that A0 is TC. Easy. And now we can stick that into the time-symmetric conditions, the time-symmetric slice version of the conditions. And first, we'll consider proper subsets of the universe. So chi being the co-moving coordinate ranges up to pi, and pi is the entire universe. And so if we consider a proper subset, and we stick in what we found for A0, and rewrite all of the various constants in terms of Tc and L Planck and T lambda, if it were relevant, then we find that the first condition reduces to this condition here. So you can see the ratio of the volumes to the area needs to exceed this ratio of constants. But we're also restricted to being in the semi-classical regime, and so we already have a condition on that ratio of constants, so this needs to be very large. And so you can see that, well, maybe you can't see this if you don't know by heart the closed volume equation and the closed area equation, but the volume in enclosed geometry is 2 chi minus sine 2 chi with some factors of pi, and then area is sine squared chi. And so if you look at this ratio, just believe me that it is large at large chi. And so this condition will be satisfied if chi is large for the island, so the island is nearly the entire Cauchy slice.
You don't need to know the formulas, right? It's just a statement that if you look at nearly an entire sphere, the volume goes to some fixed number, namely that of the entire sphere, but the area that you're dividing by goes to 0 in Rn.
That's true. Yeah, I guess it's still true in closed geometry.
And otherwise you just have an order 1 regime.
Yeah. And then the fourth condition, if you remember, the fourth condition was the complement of the first condition, and we're looking at proper subsets, so the fourth condition is relevant here. So then the fourth condition just ends up being the complement of this condition, where complement, I mean, is the same condition, but with chi replaced with pi minus chi. And so this fourth condition will be satisfied, again, restricting to the semi-classical regime, will be satisfied if that complementary region G is also nearly the entire universe. So you can see that these seem like they're incompatible, because we can't have I being almost the entire universe and G being almost the entire universe. So it looks like proper subsets in the closed universe, lambda equals 0 case, do not satisfy all of the island conditions, the necessary conditions for islands. So next we can ask about the entire Cauchy slice. And just like I said at the beginning, the entire Cauchy slice, having no boundary, trivially satisfies all of the relevant conditions. So that's conditions 1, 2, and 3. And so it is a viable island candidate. So then we can ask, since the entire Cauchy slice is a viable island candidate, is there a reference region for which it is an island? And that would require the entire Cauchy slice to be better than the empty set, so better than no island at all. And by better, I mean the generalized entropy is smaller, because we're trying to minimize it. And so that will be true, you can see from this, that will be true in the case where the reference region is more than half of this reference spacetime, MR. So yes, the entire Cauchy slice is indeed an island if we choose R to be large enough. So in summary, for the closed universes, lambda equals 0 case, the proper subsets didn't satisfy conditions 1 and 4 simultaneously, so they're ruled out. And then the entire slice always satisfied all the conditions, and here's an example island.
Is the entire slice, the false condition is 0?
Hmm?
Is that 0?
The area, well, it doesn't have a boundary, so the area is 0.
Yeah. But G
What was
is
the question?
also not there. G is no.
G,
So G is 0.
yeah, I guess it's kind of phrased strangely, but the entire universe is quantum extremal, and those two conditions are equivalent to quantum extremality.
And
So maybe good.
literally taking S of G.
There's no G, there's no G there.
Yeah.
The
so
fourth
S of G is
condition,
0.
pertains to the question of whether.
I thought I was asking about the third condition.
Oh,
Is that what you're asking about? The third?
No.
Oh, the fourth condition is just not relevant here, because the fourth condition is only in the case where you're looking at a proper subset of a closed universe.
Okay,
And so it's not relevant for this.
You can just extrapolate with the 0 bigger than 0.
Yeah, okay, I see, yeah. So just for comparison, in the flat FRW case, the results from that other paper were that there were no islands possible in this case with lambda equals 0. So yeah, and I should say the lambda equals 0 and flat case.
Because it's a necessary condition, you may include equal sign there. You don't have to say. No, in the fourth condition, if you include equal, then you don't have to say it applies.
Oh yeah, yeah.
Well,
I guess it's.
Then you have to worry about cases where there are two equal island candidates.
But it's a necessary condition anyway. But
Which are highly non-generic, and we decided not to worry about.
So now let me show you the lambda less than 0 case with closed universes. It's slightly more complicated, so I will show it. So again, we have to find A0, and we could look at the case where the complementary region for this one here. So here, A0 is approximately the square root of T lambda Tc if you assume that T lambda is less than or of similar order to Tc. You could look at the complementary regime, but that would be the case where lambda isn't really playing a dynamical role. It's really late. And so that would results we would expect to be the same as the one we just did. So
There is no dynamical role if T lambda is large.
yes, no. So that's why I'm saying we're looking at this regime here, because if we looked at the other regime, then the results should be the same as the one we just did.
Which was lambda equals 0.
Yes.
Ah, thank you. Okay.
Yes.
Sorry. Yeah,
Okay. So now let's see if all of the conditions can be satisfied for proper subsets first. And if you go through the same procedure, sticking in A0s, all the volumes, and all of the various different collections of constants, you'll find that the first condition will reduce to this condition on the volume to area ratio, where the volume to area ratio needs to exceed this alpha, which is a collection of constants here. And condition 4, again, with, I guess, the benefit of hindsight, we know that condition 1 and condition 4 are going to be related. But condition 4 gives the same condition, but with chi replaced by pi minus chi. And so if you solve this exactly, then you'll find that there is some critical radius for which this condition is satisfied, and then there is also a critical radius for which this condition is satisfied, and together, the chi will satisfy both of these conditions if it falls within this range, where chi1 is the critical radius that comes out of this first condition here. So it turns out it's just, I mean, maybe it's kind of intuitive, but they're just complements of each other, so you just end up with this range, chi1, and then pi minus chi1. So,
okay, in a case with lambda equals 0,
yes.
you were very quick, but you just said chi1 is bigger than pi over 2, or something.
Chi1,
Something corresponding. I mean,
here, wait, let me go back.
Do not overlap.
Yeah, that's right.
That was
But
very quick.
this, you made it sound like this chi1 always exists in this, in the lambda.
One is kind of, one is preferring one side only, and then the whole prefers the other.
Yes.
And didn't say that there is no overlapping region.
Oh, well,
It says in the last line, but
wait, so what's your question? Could you say it again?
but these two conditions are satisfied in different regime, right?
Well,
Condition 1 is satisfied when I is big,
yes.
and condition 4 is satisfied when I is small.
Well, it's satisfied, I guess it's satisfied when G is big.
Yeah, so
But
I
then,
is small.
yeah, but, yeah.
So then these two regions does not overlap. It's
Yes.
something you need to say to go to the last line, right?
Yes.
Maybe obvious, but it's
That's
Well,
definitely
wait.
the last line, right?
That's what I meant by this last
yeah,
line here.
It's stated, but yeah.
Well,
I think we
I
have
th-
a
I
lot of
think-
agreement here. I'm not sure what you're asking us, this is exactly
it does
the
need to
point
be
of
more
this
than
course.
half, if that's what you're asking.
Okay.
Yeah. So I needs to be more than half, and then G also needs to be more than half.
Yeah.
Yeah. Okay. Yeah. So.
That's what I meant by over 2.
Oh, I see. Yes. Okay. Going back to the closed universe negative lambda case. So these conditions, yeah. So in this case, they aren't mutually exclusive, and there is an overlapping region where both of them
But
could be.
not for every value of alpha in this extreme, right?
Yeah, I guess, yeah, once alpha gets outside of a certain range, then they'll stop overlapping. Yes, that is true.
I mean, you're in a regime where T lambda could be comparable to TC.
Yes,
But you
it
cannot
should
find
be
a
ruled
chi1
out.
in that area, right? You need to be in a regime where T lambda is much, much less than TC.
Yes, yeah, I guess I didn't put that up here, but yes, that's true.
Right? And the reason for that is that the second factor in that expression for alpha is very large. But for the condition 1 to be satisfied, alpha can't be much bigger than some order 1 number. So you need something to make it small, and that's T lambda over TC, the first factor in the definition of alpha.
Yeah. Now we do have to check condition 2 and 3, and under the time symmetric slice versions, and then putting in the A's that we found, you'll find that the conditions reduce to these. And again, these are satisfied in a particular, they're both satisfied together in some range of chi. And you can show, I have to do it numerically, but you can show that chi2 is always less than chi1. And so conditions 1 and 4 are more stringent than condition 2. And so all of the conditions together will all be simultaneously satisfied in this range, with the caveat about the size of alpha also, which I didn't put up here. So we'll move up the result up to there. And now look at whether any of those island candidates could in fact be islands. And yes, they will be islands in the case where, of course, you picked the appropriate size of chi, and then you choose the reference region to be the matching region in the reference spacetime. So those are proper subsets. And then you can also ask about the entire slice again. And just like before, it's going to trivially satisfy all of the necessary conditions and be an island candidate. And it will be an island. Again, we have the restriction that we have to pick R to be more than half of the reference universe, or the MR. But we also need condition 4 to be violated because the entire slice is now also competing with the subsets. And the subsets aren't better than the entire slice in the case where condition 4 is violated. So we also need to pick the appropriately sized chi such that condition 4 is violated for the entire slice to be an island for that reference region. So just a quick summary. In the proper subsets, we found that all the conditions were satisfied for some range. And we give an example of the island. And then the entire slice, again, always satisfies all the conditions, but is now competing with the subsets and is an island. Here's an example of an island. So that's kind of how the procedure goes. And I'll show you the results for some of the other cases here, the rest of the cases. Oh yeah, also, here's for reference. For the flat FRW analysis with lambda less than 0, they did find that islands were possible if they were large and near the turnaround time. So I'll just, yes.
It's like continuation of the flat FRW, so the curvature still has to be much smaller than lambda, or something like that, or T lambda has to be much smaller than the turnaround time, which is dictated by the fact the universe is closed.
Yes, T lambda does have to be, if T lambda is too large, then you just get the results from lambda 0, which is no islands. And then, what was the rest of your question?
Okay, so yeah, basically it's because it's curvature.
For the proper subsets.
Yes.
For the entire slice, that
Yeah.
doesn't matter.
Okay, so how do you find this matching region? It's R, this matching region. How do you identify it?
So I guess you have to. So the original construction was 2 copies of the same space-time, and then you did the conformal transformation. Basically, just undo the conformal transformation and then look over here and find the matching region.
The thermal field double gives you more or less local pairs of local entanglement between radiation in the same regions. So they purify each other, and that's beneficial over an island.
So then I'll just show you the results for closed universes where lambda is positive. And in that case, you'll find that conditions 1 and 4 together violate the semi-classical regime. So proper subsets are a no-go. And then the entire slice, just like before, always satisfies all the conditions. And example island is, again, the case where the reference region is more than half. Oh, that should be, yeah, the reference region is more than half of the reference second spacetime. And then comparison to flat space. So now I'll turn to open universes. And the first case to consider is lambda being positive or equal to 0. And this case is going to be eliminated very quickly because when you try to find the turnaround time, there are no time symmetric slices. And so that's just a non-starter. So no islands in open universes with lambda positive or equal to 0. And then the final case is open universes with lambda negative. And if you do the same kind of procedure, except condition 4 is now no longer relevant because you're looking at open universes, and that was only relevant for closed. But if you do the same kind of procedure, you'll find that the conditions are simultaneously satisfied for chi that are larger than some critical radius, which I'm calling chi 3, as long as you're in this regime here, So otherwise, you find that the first condition will conflict with the semi-classical regime. And then you can check to see if such an island candidate is in fact an island. And yes, it is, if you pick the island candidate to, of course, have the appropriate radius and then choose the right regime, then it is an island for, again, the matching region on the other spacetime. And I tried to denote that these were open universes by making the edges fuzzy. So they're not closed. They might look like they're closed because I drew them as circles. And then compare the flat space. Islands are possible with negative cosmological constant in the case where if they were large and they were near the turnaround time. So now I'm going to just put up a table with the summary of the results. Prepare yourself for a lot of text. Here are all the results. So you can see, I just summarized them here. I guess I'm not going to spend too much time on this slide, but if you're looking back at this and want to see a summary of all the results. You can see that the entire Cauchy slice is always an island candidate for closed universes. And then there are some particular cases where we have potential island candidates that satisfy all the conditions. And so let me just make a couple observations and conclusions based on what we found from looking at all these different cases. So the first observation is that curvature does seem to be important. Even if it's just a small amount, it does seem to change the results in interesting ways. For example, if you have any amount of positive curvature, that's always going to guarantee that the entire universe is an island candidate. And it also allows that new class of islands that I mentioned with that fall into that range, the appropriate chi range. Also, a small amount of negative curvature, not arbitrarily small, but a small amount of negative curvature eliminates the cosmological islands that we found in the flat space case. So that does seem to be important. And then another observation, I'm not sure how significant this is, but in both the cases where it's mattered, condition 1 and condition 4 together, or just condition 1, was more stringent than condition 2 and 3. So there might be something significant there, not sure. And another observation is that in closed universes, there is now a maximum island size because of that fourth condition. So that wasn't the case in the flat space case. So another question you could ask, so our motivation for our paper was primarily just to extend the results from the Hartman et al. Paper to a broader class of cosmological models. You could also ask how the results are related to our own universe, and then you need to think about the observational constraints that you see. So the universe is consistent with, the visible universe is consistent with spatial flatness, and there's a positive cosmological constant that we've measured. And then we know that on small scales, homogeneity and isotropy are violated where structure exists. And so you could ask whether, or how these are related to our results. If our results say something about our own universe. And we were considering closed and open universes, but as I just argued on the previous slide, it seems like even a very small amount changes the results. And so if there was curvature that's on a scale that's too large to be seen in the visible universe, our results would still be important to consider. And then we do measure the positive cosmological constant. We talked about positive cosmological constant cases. The other cases might still be relevant if you have a theory with multiple vacua, and then it's possible that the universe could decay into one with negative cosmological constant or zero cosmological constant. Then the other results would also be important there. And then you could ask if the homogeneity and isotropy violation might affect the results. So where this appears is in the assumption that we were using FRW universes, which are homogeneous and isotropic. And you could ask whether this violation should affect the results. I think no, because in order to satisfy that first condition, where the matter entropy needs to be larger than the island size, or the area cost, that's going to only happen on a very large scale, a large scale where the FRW approximation is a good approximation. But you could ask, I have this as one of the open questions, you could ask what happens if you drop the large-scale homogeneity and isotropy assumptions. We didn't do this, and so that's an interesting question that could be looked at.
Other people,
Yes, in fact. And you could also ask, we kind of skirted the problem of what could produce the entanglement required for islands to be favorable, and could ask what could be that dynamical source of the entanglement. And then finally, perhaps the most important question, which you don't really have a great answer to, is why does it matter whether islands are possible in a particular universe? With that, I will thank you for your attention and welcome any other questions now.
You have questions for us? Please, I have a simple one. It seems like you're talking about 4 dimensions for the type of space-time. Right?
Yeah.
Do you think anything would change for higher dimensions? Or maybe just the numerical values, but not the possibility?
I don't see, off the top of my head, a reason that I think I'd want to try it and see. I don't see a reason that it would change the results right away. Yeah, I don't think so.
Whether non-trivial islands is because entropy rose, well, let's go to the flat case, right? And the entropy grows with 1 higher power than the area, but with a smaller coefficient, so that's why you need a very large region. But that'll always be true, right? The whole universe will be a candidate, will always be true. So yeah, I think it will affect some numbers, but not
Probably completely space. Any other questions for us? If not, let's make. Oh, sorry.
When you want to apply your particular setup to real universe, you probably estimate a spark from radiation, right?
Yes, yeah.
But if radiation is produced by reheating, then probably it's self-entangled. It's not.
It's what?
It's self-entangled within
Oh.
our own universe. So thermodynamic entropy is not really. In your case, of course, it's entanglement with whatever bath or something. But if our universe is a pure state, then it's a pretty much self-entangled.
So what's the question? Is that just an observation?
Yeah, radiation is thermodynamic radiation and the von Neumann entropy is very different. Because correlation between the photons and so on, it's just radiation is self-correlated.
I'm not sure.
Correlation is
Yeah, I guess.
coming from inflaton, inflaton vacuum correlation, and that's the correlation length. Radiation in our universe is not entangled with something else. Probably it's entangled among themselves.
Yes. So are you wondering if we could do some similar analysis where?
No, I think that would be the probably
okay.
real issue that things you.
Okay.
So, but in principle, instead of radiation, could you take any other type of energy content, like matter, inflation, whatever?
You could. I think the results shouldn't depend too much on that. Trying to remember what the contribution is for matter, but I think that the radiation contribution is a good approximation for covering matter as well.
It'll affect some numbers again.
Yeah.
Just the fact that so long as the entropy is actually extensive in the volume, basically what you're doing is balancing the entropy in a large volume against the area, which grows less rapidly. You'll have to choose an even larger volume for something like dust, where you have less entropy density, but you can still find it.
Just one comment which I like. That's the reason why we have to use some rule or something.
Oh, in your discussion?
Within the universe, the other is going to outside the universe. If you just use reheated radiation, probably entangled among themselves. it's a large region.
So generally, when you, let's say we have a closed universe, globally closed, but there's some kind of, let's say, eternal slow roll inflation going on or something like that.
Yeah, some setup.
So let's say we're doing that. I don't know if we know much about what the entanglement entropy of, let's say, half of that universe is at some time. In particular, the reason I think we don't know much about it is because the entire picture that we use when we do eternal inflation is sort of inconsistent with the coherent evolution of the universe. Right? Maybe I should have taken actually bubble notation, like multiple vector. Like where those bubbles nucleate, whenever we draw a picture of bubbles nucleating here or there or the other place, we've already decohered this somehow, which is actually a bit shifty because, you know, it's not clear that there's a good environment, right? So as soon as you draw a bubble universe in one particular place, it's not even clear how to do a coherent analysis of where the entropy is. And I think that's actually, that's actually a pretty big
So
problem.
that's why I was saying, in a specific case, if you want to identify this radiation as radiation from the heating, then the origin is in film, and you know the radiation length. And
Well,
but it is,
I think we can understand why it seems decoherent to us. But to do this analysis, you take a kind of global viewpoint, right? And I'm not sure that there exists a good global viewpoint in which there's a specific history of the universe of